If we observe a cup of hot coffee, we can feel the heat coming off of it. Because of the temperature difference, heat naturally flows from the coffee into the surrounding air. Sometimes you can even see it, the faint steam rising, almost like the coffee is giving something away. While that temperature difference exists, heat is flowing, and heat flow has the potential to be used to do work. Now, imagine we place a device between the hot coffee and the cooler air. Not a real one necessarily, just something that could take advantage of that flow. It would take in heat from the coffee, reject some heat to the surroundings, and convert part of that flow into useful work. We can describe this process using a simple relation. Net work on the device equals amount of heat in minus amount of heat out, or W equals Q in minus Q out. This is the work we get, which is part of the heat flow we're able to keep. But now, let's wait. As the coffee cools, that temperature difference begins to fade. The heat flow becomes weaker, until eventually, the coffee reaches room temperature. At that point, everything becomes quiet. No visible heat flow, no movement, no change. Now, if we tried to place that same device there, it would produce no useful work. Essentially, W equals 0. But we must think, if the same energy is still sticking around, and we know that energy can neither be created nor destroyed according to the first law of thermodynamics, and yet nothing can be done with it, then clearly, energy alone is not the full story. Let's consider something more practical. In the late 1890s, Frank Schumann developed one of the earliest practical solar thermal systems, called the sun engine. His system used mirrors to concentrate sunlight onto tubes carrying a working fluid. As the fluid heated up, it produced vapor that was sent into a low-pressure steam engine. The expanding vapor pushed a piston back and forth, and that motion was used to drive an irrigation pump. Even though this looks very different from the cup of coffee analogy, the same idea is at work. The hot coffee is like the hot working fluid in Schumann's system. The cooler room is like the cooler surroundings and the condenser. And the imaginary device we placed between them is like the low-pressure steam engine Schumann used. In both cases, heat flows from something hot to something cooler, and that flow is used to produce work. So if we were building a real system like this, the key question becomes, how much useful work can we get from that heat flow? That is where the idea of exergy comes in.
Exergy is the maximum useful work that can be extracted from a system as it comes into equilibrium with its surroundings. Not the energy present, but the portion of that energy that can actually be converted into work. To find that maximum, we return to the device we imagined between the hot coffee and the environment. Even in its most ideal form, where nothing is wasted, no energy is lost to friction, and every step could, in principle, be reversed, it cannot convert all incoming heat into work. This represents the best any heat engine can ever do. Some portion must always be rejected. The question is, how much? The answer comes from entropy. Every transfer of heat also transfers entropy. For a quantity of heat Q flowing at temperature T, the entropy it carries is Q over T. Notice something important here. The same amount of heat carries more entropy at lower temperatures than at higher ones. This is why high-temperature heat is more thermodynamically valuable. It carries less disorder per unit of energy. In the ideal device, no entropy is generated internally, so whatever entropy arrives with the incoming heat must leave with the rejected heat. Q in over T equals Q out over T0, T0 being the surrounding temperature. Q out is the minimum heat that must be rejected, even under perfect conditions.
Substituting into our work equation, maximum work equals Q times 1 minus T0 over T. This maximum possible work is the exergy, X. The term 1 minus T0 over T does all the work here. It is the fraction of incoming heat that can actually become useful work. When the source temperature T is much higher than the surroundings T0, that fraction approaches 1. Most of the heat is convertible. As T falls toward T0, the fraction shrinks, and when T equals T0, it becomes 0. The energy is still present, but none of it can be extracted as work. Let's take a quick example. If I have hot coffee at 350 Kelvin in a room at 298 Kelvin, 1 minus 298 over 350 is approximately 0.15. Only 15% of that heat could ever become useful work, even under ideal conditions. Up to this point, we've been thinking about an ideal situation, a system where heat flows from a hot source, part of it becomes work, and the rest is rejected to the surroundings. But real systems don't behave that cleanly. Heat doesn't stay exactly where we want it. Some of it spreads into the surroundings before it can be used, and any motion we try to extract faces resistance, friction, imperfections, or even material limits. None of this destroys energy. The total energy is still there, but they change how that energy is distributed. And work depends on how concentrated and directed that energy is, not only how much of it exists. So to understand what's being lost, we need a way to track how energy spreads during a real process. Entropy comes in. Again,
Entropy is a measure of how spread out energy becomes. When a quantity of heat Q leaves a source at a temperature T, it carries entropy, Q over T. When that same heat enters the surroundings at a lower temperature, T0, it carries Q over T0. Because T0 is less than T, the surroundings gain more entropy than the source loses. That difference is created during the process itself. We call this entropy generation. Entropy generated equals Q over T0 minus Q over T. This value is always positive, a direct consequence of the second law of thermodynamics. Now focus on what this means. That extra entropy wasn't there at the beginning. It was created during the process. And physically, it reflects energy becoming more spread out within the surroundings. At this point, we connect that spreading back to something measurable. From thermodynamics, energy and entropy are linked through temperature. So if the surroundings are at temperature T0, an increase in entropy corresponds to an amount of energy equal to T0 times that increase. That means the energy associated with this newly generated entropy is T0 times S gen. This quantity represents energy that is still present but no longer available to produce useful work. We define this directly as exergy destroyed. The entire picture of any real thermal system becomes exergy in equals work out plus exergy destroyed plus exergy out. Some of the available energy becomes useful work, some leaves with the rejected heat, and some is lost in form of usefulness due to irreversibilities in the process. As energy is transferred and spreads into the surroundings, a portion of it becomes unavailable for work. The usable portion is exergy, and its loss is what ultimately limits every real thermal process.